Yeah, it's kind of like it is almost like a champion and then like I was totally sorry. Yeah. Not viral possibility. But they'll be working there for more than solution. I bet it's not. $50 different. My dad, they didn't give me ideas yeah, yeah. So when I started my job, I was honestly, more yeah, I mean, practically that makes sense. So for us, it's better yeah.
Okay, so for today's class, the plan is that we will continue with the data and labeling data. And then we will have series of labs. So we will start with some labs around like a containerization and like a Dockers. And then we will basically start a lab with data version control. And then we will start a lab with data, like a data pipeline orchestration using Airflow. Okay, so that will be the idea for today's lab. So I'm not letting any student in the Zoom. If any of your friends is trying to join via Zoom, tell them the class is not via Zoom. Okay, they need to be in person or watch the class online. The recording. All right, so we are going to continue with the labeling, and we are going to first start with the case study around model performance degradation. So let's assume you are a retailer. I'm gonna wait for your friends to sit. Let's assume you are a retailer and you are selling shoes. And the way that you decide how much basically inventory you need to have for each types of shoes, you have some machine learning model that takes into account something like click-through rate and gives you a prediction. For example, this shoes is going to sell because it has lots of people clicking on it, you know. So you have some model that makes that prediction. and you use that to order inventory. Now, let's say all of a sudden your basically model performance drops. That means, what does that mean? That means you order lots of shoes and no one buys them. Or you didn't order from certain shoes and everyone wants that shoes. Okay, so that's what it means when model performance drops. Now, the question here for you will be that, why? What did happen? Okay. And how do you know what's the problem? Okay. So when it comes to ML models, if we don't have a system in place, if you don't have a system in place already, if you are not logging or monitoring for certain basically data, certain information, when something like this happens, you're really blind to the problem. What was the cause? So you need to basically take the data, go manually, try to understand what was the cause of the problem, because you didn't think ahead of time, right? So the idea here is that how could we monitor, or what should we monitor when we build a model, so we are able early enough to detect if something is going wrong, okay? So we are going to talk about how to detect problems early on, what are the possible causes, and what could be done to, solve these problems. When it comes to problems, and especially with machine learning problems, there are two types of problems that you deal with. One is called like a slow problems, or like something like a drift, your model basically drifting. And the other one is like a fast problems. When fast problem is something like all of a sudden sensor is wrong or doesn't work, or the light on a manufacturing basically is off, or you have done some update. Like let's say your pipeline using someone else's model, like is hierarchical, and due to some updates, those are not compatible anymore. Those two, something all of a sudden breaks. So it's either a slow problem or it's kind of like a sudden problem or error that you have. When it comes to a slow problem, gradual problems, there are two types of problems that you deal with. Data problem, or it's data changes or word changes. Most of the time is actually is on the first one, but we'll talk about it. Data changes. Data changes are something that happens basically gradually over time. And they could be like because of some trend or seasonality. They could be because some distribution of your feature has changed, or it could be some relative importance of feature has changed. What does that mean? That means previously, when you built this model, when you did your analysis or study, you found out, for example, height is really important to detect something. But as you collected more data, new people come, new data comes basically, or new, basically like a new region, for example, you have touched, or you deployed your model for new different age groups, you all of a sudden notice that height is no longer important, right? Because it was previously important as part of your training or basically evaluation, but it's no longer important. That becomes something like as a gradual data changes. When it comes to word changes, word change basically means that all of a sudden, you are selling shoes and, the style has changed. No one wants that shoe. So it's kind of like something outside of your model scope, but it's a reality also. Or the scope and the process has changed. The competitors has changed. Like previously, you didn't have a competitor in the market. All of a sudden, you have competitors. Like right now, ChatGPT and DeepSeek, whatever is going on, right? So, or business expands to other geographics that you built your model for a certain geographic, but now all of a sudden the company decided to sell it to a different geographic, and you didn't train your model for that. Your model will not basically perform the same that it used here versus in other country, because the data that he used was primarily from here, right? So when it comes to sudden problems on the other end, you either have data collection problem or you have system problems. Okay? So data collection problem is that when you have bad sensor, bad camera, bad log data, something was moved or disabled, like a cameras or some sensor, for example. When it comes to system problem, you have software updates that could cause a problem. You have network connectivity, like all of a sudden the network is not basically working. Your system could be down, or bad credential, which is actually, if you read about IT problems, bad credential is actually one of the top issues that IT deals with. Like someone forgets a credential to enter bad credential. So these could be sudden problem. There's additional sudden problem also, like if you think about when COVID happened, that's also a sudden problem, right? So that also, it could be a combination of some sudden word change plus data change, basically. Okay. Now, why is important for you to understand your model? Okay. Because the first thing is that, let's answer, can anyone tell us what does understanding your model means? What do you think it means to understand your model? Kind of, what else? That's correct. What else?
I mean, if it's an AI model, it's explainable in some sense, like we understand why certain maybe neurons are firing and kind of like how it's interpreting the data as we go along the process.
Yeah, so these are all correct because the idea here is that understanding your model is that to understand how is your model's behavior based on the data. You know, it's like if I perturb some data, what it will change if this types of data comes and the model makes this decision. Can I explain what's that decision was or why what it took that basic decision? And the reason for that is because first, you know, misclassification doesn't have a uniform cost. You know, it's just from development perspective, maybe it's all the same cost, but from the end user, it doesn't have a uniform cost. If you think about, for example, if you're in healthcare and you make a prediction for disease, if you tell somebody that they don't have a disease or some like for example cancer and they have it, that cost is really large. Versus if you tell someone that they have a disease and they don't have it, that cost is almost pretty low because they take another test and comes out negative. The other one is that the data you have is really the data you wish have, and also, we know that the model objective, the objective that you use for training a model is always a proxy for the business objective. The company wants to, sell more, monetization. But when you develop a model, you cannot use that as a metric for developing your model. So you use a proxy to train this model, and the company which you are trying to map that proxy to the business goal. So now, if the business goal doesn't meet, you cannot do a direct mapping because you were using a different metrics. It's really important for you to understand, that's how my model behaves. And also, it's reality that some percentage of your customer will have bad experience. Your model won't work the same way for everyone. And the last one is that the real world does not stand still. Just again, it's a really interesting saying which says that the only constant in word is change, right? So that's always happens. So now, data and concept change in production ML. So let's delve into this one. We're going to first start talking about the detecting problems with deployed model, which is going to be data and concept changes. And then we're also going to talk about the changing in the ground truths. There are three types of problems that we can basically look at: the easy problem, harder problem, and really hard problem. The categories could be easy, medium, hard, doesn't matter, the wording here. So when we are talking about detecting the problems with a model that you deployed, you could have, for example, data and a scope that's changing, and we will see how we can monitor those. And your goal is that in order to detect this, to monitor your models and validate the data that goes through your model and to detect this early enough, right? So if I have a model and I have a pipeline for this model, and I want to see that if the data is changing as part of this pipeline that you have, every time a new data comes, you compare this data with some statistic and some schema that you have, and you create some sort of like a percentage of change or frequency count, some metric for yourself, and you put a threshold. If over a certain period of time, the amount of like a weird data or new data that I'm receiving is more than this percentage or this amount, then I have some sort of like a data drift, right? So that could be one way. And the other thing is that changing in the ground truths, that means that, changing ground truths as example of when the COVID hit, right? So like all of a sudden, all those transactions that they were marking as fraudulent, they are no longer fraudulent, right? So if something like that happens, so you need some label for the new data. because you cannot use the previous data because previous data was labeling those transactions as fraudulent, and right now you say it's not fraudulent, so you couldn't use that. So you need to label new data. Now, when it comes to the label issues, you know, the new, basically the label changes, the easy problem is the scenario is that when the ground truth basically changes slowly, maybe over a month or over a year, okay, that becomes something like an easier problem. Normally, if something like that happened, the model retraining, you retrain your model based on two things. One is you want to do a model improvement because you have received new data, right? You want to improve your model. And the second one is that you have some changes in your software or in your system, which you know because of that, I need to basically retrain my model. Okay, so it becomes a gradual trigger for model retraining. And the data that we basically acquire for this task comes from either curated data set or some sort of like a crowd-based data set. Think about a scenario like in fashion, right? So certain fashions that, you know, I don't know, maybe every 6-7 months, something like that, you see something changes. Like maybe something was categorized as like always like a fashionable, and all of a sudden it basically is no longer fashionable. So the ground truth for that item will change. And it's not as sudden. It could be in 6 months or it could be in a year, for example. So there's certain things that basically they change, you know, like a much slower. Then you have harder problem that when, you know, when the ground truths change faster, like over the week, you know, could be all of a sudden. And normally this happens when, you know, it's just you have some declining in model performance, you have some data you want to improve your model, or you have some change in software. But the main reason normally is when you have declining in model performance. It's the idea of same thing that think about in inventory. You were basically doing the inventory and you're ordering certain product, and all of a sudden these two types of shoes, for example, become really popular, or no one buys them anymore. So then you have basically decaying in your model performance. So you use that knowledge or you use that as a trigger basically to retrain your model. The data that again you can acquire for this task labeling could come from direct feedback and crowd-based. And who knows? We talked about it before. What's direct feedback? Feedback from user, right? So if basically like you recommend the user buy these shoes and they buy it or they don't buy, or they click on it or not, that you can collect that as a feedback that is no longer important for them, right? So, and you have really hard problems, really challenging problems, and when the ground truths change really fast, days, hours, or sometimes in minutes, right? The main one that you can always talk about is the stock market, right? In stock market prediction, it's pretty hard to address, you know, it's just kind of like, because it fluctuates a lot. There are certain timestamps that you always can predict ahead of time because it's kind of like a linear, and then after that, if there's a drops down, up, this is kind of the fluctuation is really bad, right? So when you deal with something like a stock market, you know, the declining model performance is always the main reason for triggering. And again, you could have other reasons you want to improve your model, but you need data for that. The data comes from direct feedback or something called weak supervision that we're going to talk about today. So it's actually interesting. So if you look at how in the stock market, the models basically being used, so the model retraining is pretty more basically common than any other basically fields. It's possible that you retrain your model every hour, for example. Like your model constantly updates itself, because why? The data that you're basically looking at a much shorter period of time making prediction. So maybe you only need a window of like a half an hour to make a prediction. So every half an hour basically data, you pass it and you use it for retraining a model, right? So if you're in a domain like that you need to update the model that quick, you also know that, well, I cannot use really expensive models. Should be pretty cheap models, you know, something maybe just some sort of regression models that I can quickly update them and every half an hour, so it doesn't cause me lots of cost, right? So that's one of the things about the stock market. And again, I don't know if any one of you has planned to do a stock market for the project. Is anyone here? No? All right. So now let's talk about first process feedback and human labeling. Okay. When you want to label data, there are different basically methods that you can use. One of them is process feedback, as your friend says, stuff like some sort of like a direct labeling. So you give user an answer. If they like it or not, you try to collect that feedback as as your label. Or you use human labeling. Basically, you hire raters and you pay some company or some hiring you do yourself, and basically to use that for labeling. Then there are more advanced techniques, semi-supervised labeling, active learning, and weak supervision. We will have those later. First, we will focus on the top two. But if you want to just quickly just tell you what are these. So semi-supervised labeling is kind of like you have small amount of label and you have lots of unlabeled data, and you try to basically use some sort of model to learn a knowledge from labeled one and apply it to unlabeled data, to just label those. And we have active learning, which is the type of labeling is like, instead of, so if your model is performing bad on certain tasks, active learning says that instead of just going collect data for everything to like a label of data, label lots of new data, only look at the portion, look at the parts that your model didn't do good, and be more intelligent about what I should label. Basically, to look at your model and see that which data I should label, which can improve my model more than others. That's the idea of active learning. So instead of labeling lots of data and basically train your model, and you only look at your model and see that where it doesn't perform good, and among those parts, which one is better for you if you label. If you think about the example that we had, that rubber sheet basically idea, cafe noise, restaurant noise, and stuff like that. So instead of labeling all of those data, you picked one of those because you were like, if this was the worst than the rest, if I improve this, I think it's going to also impact the rest of those. That's kind of like intelligent sampling, right? That's the idea behind active learning. Then you have weak supervision, and weak supervision is something like, it's like an ensemble approach, like when you hear the idea of weak classifiers. That's the same idea. So instead of basically having a long pipelines for labeling, you create series of small labeling functions, and you let the data go through all of these, and you do aggregated vote among those, or you basically combine those. Let's say I have 10 functions that they do, every 10 that does labeling. Then I basically get the output of those 10, pass them to a regression or logistic regression or linear regression. So each one of those will get a weight based on how important they are, and I use the output of those as the final label. So that's the idea of weak supervision. And we're going to have more documents on that soon. Now, so when it comes to process feedback and human labeling, again, process feedback becomes actual versus predicted click-through, and human labeling is that if you hire a doctor or cardiologist and says that, hey, label this MRI images for me. And why labeling is important in production ML? Because the first thing is that there are lots of data available. Any company that you go work, the main thing that you have is actually unlabeled data. As always, everyone collect data, you have lots of unlabeled data. And if you want to be able to build new businesses with those data, you need to somehow label those data in case you're doing something supervised, right? The other thing is that frequent model retraining. Your model needs retraining. And if you want to retrain, you need to have a new data labeled, right? So if you, let's say you have the perfect pipeline for model retraining, but you never thought of labeling new data, right? So basically that pipeline doesn't do anything, right? You're basically using the same old data every time. And then also, that should be somehow some sort of like a task for you, a goal to create a new training data set. Now, in direct labeling, the idea behind that you can basically implement is that you have some basically data that comes from the user. That data goes to your model as an inference, okay? And your model make a prediction. You show that prediction to the user, and you see basically what users' behavior like, if they like it or if they repeat the question or not. based on whatever feedback you get, you bring that feedback and you append it back to the data that you have and you continue. It's kind of like an updating loop. So you make a prediction, you get users' data, make a prediction, you see their reaction. If they give you a label, you bring that label, add it to the data that you had. Now that goes to your historical data and some sort of like a loop, right? So that's the idea of like direct labeling. It has some process, like some advantage. Basically, it's you can easily create data. Labels evolve quickly. It can capture strong labeling signals because you get the labels from the user exactly. It has also disadvantage. It's basically it's hindered by the inherent nature of the problem. It's largely bespoke design. It's like you cannot have the same design for everywhere else. It's kind of like that. And it's also easy to failure to capture the ground truths because you need to also keep in mind that what user think is the correct answer is not necessarily is the correct answer always, right? So it's kind of like you need to account for those noises that user will introduce by labeling for you. Now, if you are trying to work with process feedback, that means you're trying to get the user's feedback and somehow use that as an information for labeling. You need to have some system that you can parse those information. Most of the time, majority of time technically, you collect logs. So the feedbacks and everything that you receive is comes as some sort of logging, basically, right? So and you receive lots of logs depending on especially how your model performs. If, for example, if you are doing an online model, that means every moment the user works with it, you keep collecting logs. So you're going to deal with lots of logs, and so you need some sort of system in place that you can get those logs, basically parse the logs out, pick the important information, maybe add them to some sort of a relational database, so you can use that information for downstream tasks. So there are a couple of tools that you can use. One of them is called Logstash, which we're going to work with in this class, and the other one is like a Fluentd. Okay, so both of these basically are some sort of like some libraries that I don't know about Fluentd, but Logstash is like a free libraries that it's just stashing the logs that you're receiving is pretty like it's pretty easy to work with. And if you are doing this like a cloud-based, like means if you're writing your logs to the cloud, both GCP, AWS, Azure, they all have a perfect basically logging system. And I think on AWS, basically, you can use the Logstash. Sorry, on GCP, AWS works with something called Elasticsearch, which we will have a lab on that. I think at the end of the class today or the next class. And Azure Monitor also is another basically way. So now that's the idea of direct labeling. So you just need collect logs, get those logs, parse the logs out, and append it back to your input data that you receive from the user, and then append that to your data set that you have. And then you monitor for that data set, and if certain thing happened, like a model decaying or something happened, then you return your model using that data set. Now, when it comes to human labeling, the idea is a bit different. So you need to hire raters. You give them some raw data, and basically they label the data and use that data for some downstream tasks. The idea basically for human labeling is that you have in reality you have lots of unlabeled data. You hire some people, you give them a proper guideline instruction, which we talked about before. Then be sure that this divide your data among multiple basically raters, like for each data point. Now, the advantage that human labeling has, it's you can get more labels, and it's purely supervised basically learning because just you have people that exactly do the job for you. The disadvantage that human labeling has is it's first the quality or consistency is not the same. Like raters, they don't perform the same. They don't label the same. It's pretty slow. It's because you ask people to manually label the task for you. It's pretty expensive. And you normally end up with a small curated data set. You can make a large data set because it's pretty expensive and it's slow. Why quality consistency is not the same? It's like, again, if you think about it, you ask let's say you hire like some students and you say that, hey, label this data. Some students might be more like a perfectionist, there's like or they know a lot more about the topic, so the label is more accurate, and some of them is like they have an idea but they don't know exactly in detail, so the label is not going to be the same. The other thing is that time of the day, if you, for example, if you let everyone to just log in and just label for you, you will see after the first 2 hours the logging, the labeling basic accuracy drops because they get tired, right? So it's the consistency of the labels are not going to be the same thing. And this is basically the same idea as, like, again, there's a high cost for labeling. If you look at, for example, an MRI, for any raters, basically be sure that you limit the number of data points that you're allowed to label per day. And also the requirement, basically the recruitment is pretty slow and expensive for manual, basically raters hiring. So now, so we talked about that, okay, we have a way to label the data. At least for now, we talk about the two ways only, like direct feedback and using human labelers. Now we want to talk about how could we detect issues. So, but let's actually see if we can connect the dot here. So why do we label data? Because we want to label data if something happened, like a model performance went down, so I can basically retrain the model quickly. Like I have already new data, so I can retrain the model. Or company wants to build something new, so I have data ready. Okay. So let's say you keep adding this data to your bucket or to whatever storage that you have. So if model decay happens, so you can retrain the model. And the question here is that how could we detect if there is some issues? Detect for model derived or data derived, so we could use that data. Okay, so let's just start with detecting data issues. So we're going to start with two terminology: data derived and data askew. Okay, so then we're going to go over data and concept derived. We're going to talk about schema askew, and we're going to talk about distribution askew, and overall how we can detect these data issues. So what is derived? What is askew? Again, derived is any time the change happens over time. Like it's like a time-based changes, it's like a time series stuff. That basically becomes a derived. That means all of a sudden today data is starting to changing and tomorrow is getting worse and so on. So that becomes a drift. The skew on the other end, when you see a change between two static versions of your data, like this season versus next season. It's like all of a sudden there's a change, right? It wasn't a gradual, it's like a sudden change. Or the data that you use during the training and validation is totally different from the data that the customer has. As soon as you deploy it, you all of a sudden see that the model doesn't work, right? That becomes training serving a skew. Okay, so it's like there's a skew happens because the data that you have is totally different from the data that customer has. So that drift and that skews. Now, overall, if you think about any ML pipeline, you have data, you do some processing, goes to the model, you make prediction. What you want to do is that during serving, you want to basically be sure that replica the same thing, right? And replica the same thing, that means the same types of pre-processing that happened should happen. The same type of data that went to the model should go to the model. And basically, you need to monitor for this in order to detect if something is wrong. Now, but let's say your data is working fine and it just goes through your model. And this example here is that we are looking at the spam, okay, spam and versus ham detection. So you have on the x-axis, you have times of a number of days. And on y-axis, you have number of emails sent per user. Okay, so y-axis is number of emails sent per user. Blue line is the spam, red line is ham, okay? So you have this knowledge that if a user sends more than, for example, 10 email, let's say like maybe 10 or 12, something like that, then it's ham. If they send more than like a 20 or more email, it's a spam. You were using that as like some prior knowledge. But then all of a sudden, after day 40, you see an increment in both scenarios. Now, the users that you previously will tag them as not a spammer all of a sudden every time get tagged as a spammer in your system, right? So that becomes a scenario when the model is decaying, model is changing. But lots of time model change, the model performance goes down because the data is also changing, because the underlying data is changing. And that's the case. So the data has changed because the data that you previously using to train your model, like if 20, for example, or less, not spam, not that data is no longer valid. So if you don't have a system in place to monitor, to basically do a comparison, so you won't notice something like that happen. Now, another idea could be like, for example, during the training, you develop this small linear regression, for example, let's say, or logistic regression, something, and you have this green line, and during serving, technically, it should be this line, the blue line, because some of this data has shift, right? And that data shift during a classification means concept drift, right? Because the label for certain of these files, like this file, if you're looking at the green line as classification, anything below you will say it's I don't know, like a class 1, anything above here you say class 0, correct? But during serving, what you notice here is that these points above the blue, I actually need to be labeled as class 0, right? So the label has changed. So that becomes the concept, basically change, a concept drift. So if something like that happened, so you need to have a new model, basically, this blue line, right? Because the data, the model has changed. Yes.
I mean, what sort of scenario might the underlying labels of the data set?
So that becomes the scenario we talked about, like during COVID, the banking transaction. You imagine your banks, they had this line, and anything fall below it, they say it was fraudulent. Anything above, they say it's not. All of a sudden, you see all of this that they are not fraudulent. So you're like, okay, previously they were. So what you need to basically shift your model down, technically, right? So it's normally when it comes to concept change is when the label is changed. For some reason, that label is no longer valid. Or think about the concept like shoes, right? You look at certain shoes and maybe previously it wasn't called as a sports shoes, but now it's labeled as a sports shoes. At least people accept it as a sports shoes, right? So that also basically changed the label over that types of shoes, right? So now when it comes to your data, and we're going to break this down. So the first thing that you monitor for is the schema skew. And the schema skew comes back from same schema that you use in databases, right? So when you build a database, you define a schema for every feature, like what the data type should be and so on, right? Now, all of a sudden, let's say you expect this column to be integer, but you start receiving float, right? So that is a change in the schema. So it should be always integer, for example, the way that you have defined during the training. So that becomes the schema skew when the data type and basically some behavior of the model or the schema of the data, sorry, not the model, is no longer valid in compared to your training data. Then you have distribution skew, and the distribution skew could be defined as covariate or concept shift. We're going to break down that further. And we have a good table for that. So distribution skew, and you can basically look at it this way. So, yeah. Now, if you think about the data and the label, X is your features, Y is the label, right? So the relationship you have, one is that the joint distribution, which is probability of Y and X, that becomes the joint distribution between Y and X. Then you have the conditional distribution. What's the probability of this class given this input? And then you have the probability of the data itself, correct? So if you think about the classification, for example, let's say this is one class, and this is another class. So if this is class 0 and this is class 1, this data, right? This data has some distribution. So probability of X, and this data also has some distribution, condition on the label, right? But also the label itself in classification, we know that, right? So probability of Y given X. What's the chance this is a cat given this, right? But on top of this, you also have probability of X and Y, the joint probability of these together. Right? Seeing like a probability of being a cat and this is together, like these features you have. So that's the joint distribution. So if you look at the joint distribution, when you do that during the training, you find the distribution over. And the idea is that keep track of those distributions, right? So you basically have some sort of like a placeholder, you have the distribution of your training data. And you, during the serving, you get new data that comes through and you compare that new data from that distribution. If the distribution no longer valid, that means the new data that you receive, it's not part of that distribution that you have, then that means you have a data set shift. There's a shift in the data set that you have. Okay, so again, if you have a joint distribution and during the training and you have this safe, and all of a sudden during serving, the new data that you get, it's not from the same distribution. Okay, so the distribution of data that comes through serving is not the same. You will say, I have a data set shift. Okay. Now, covariate shift is the scenario when probability of X is no longer the same. That means for class 0, during the training, this was my probability of X. Okay, this is my data set for X, like the features. During serving, for class 0, any data that I get falls outside of this distribution, for example. Is no longer part of that distribution. So that becomes covariate shift. So probability of your features input are no longer the same. Then you have concept shift. Okay, so concept shift basically is that when the scenario, this one happens. The probability of label given data is no longer the same, like the conditional. Now think about what does that mean? If we say, what is the chance of being a cat given these feature sets? Okay. So, and let's say previously this was like a 90%, and all of a sudden you get new data and that drops. Like it's kind of like this conditional has changed. Probability of label given data is no longer the same. So that's different. So that becomes basically concept shift. The concept shift is focusing on the label Y given X. Covariate shift will focus on marginal of your training data versus marginal of your training features versus marginal of your basically serving or testing features. And data set shift will focus on the basically joint distribution of training versus serving. So we will see that as part of labs, and you need to do part of your product that you build. You need to, as already when you do your data pre-processing, you're building basically the data pipeline for your training data, you need to keep track of this. So over your training data, you create set of basically statistics, and every time new data comes through the saving, you compare that. If it was part of the same thing, well, it's fine. If it's not, you basically create a frequency count or some sort of like an alert system. Okay, and we're going to have this more in details. Now, there is a basically this flowchart comes from I think the idea of flowchart comes from the TFDV, TensorFlow data validation. But the idea here is that whatever pipeline that you want to create, doesn't matter if you use TensorFlow data validation or you build it yourself, need to follow something like this. So you get your training data. From the training data, you create something called first a schema. And a schema, again, you just simply could look at the column and say that, okay, if it's integer, return integer. If it's like a float, what type of float? If it's, it's like a, if it's categorical, for example, how many unique categories should be in it? Like what are the unique categories are that in it? So if you all of a sudden I see a unique category that is not part of what I saw, it's just could be a change, right? So you create some sort of like a schema, and then you go to a statistics. So you create another set of files basically as statistics, and a statistic, you focus on more getting the statistical information, like if it's in numerical, what's the minimum range to maximum range, what's the mean, what's the standard deviation, and so on. Whatever you think is useful for your case. So you create this too from your training data. So train data comes through, so you do that as part of your lab and you create it. Then you create some function, right? Something like a anomaly detection, basically. Here is it's called validate statistics. That function, that anomaly detection, the idea here is that when new data comes, like inference, during the inference, new data comes, you pass this here. So this function has this statistics and a schema, gets a new data, compares it. Based on some statistical comparison, it's not just one-on-one matching also. So for a schema, you can do one-on-one matching because it's pretty straight, but for statistics, you need to do some statistical comparison. And you basically detect, like, is either valid or invalid. Okay. And then based on that, you create some sort of like an anomaly, like a, sorry, alert, or basically, or maybe count. So we will talk about this further, but at this stage, when you detect some sort of like an anomaly, the decision of what to do, it depends on what's happening technically. So what does that mean? Let's say you, during the training, or when we collect this data for building a product, we had this scoping idea that our customers are going to be only 20 years and above. Right? So you weren't like you didn't think your idea will sell to younger generation. And so your statistic, whenever you look at your statistic, you notice that I don't know, like an age range is 20 and above. As soon as you serve the product and after, or maybe over time, you notice that your product all of a sudden becomes popular among younger generation. Okay. Now, the question here will be that, okay, if all of a sudden I get the data that's younger generation, or data that wasn't part of, like, let's go one away from the generation. Let's say country. You all of a sudden seeing country that basically were not part of your training data, but they are actually become a popular user for your product. And the question here is that, should I stop the serving? Should I not serve them? Or should I actually incrementally update my statistics and my schema and start to serving to the new customer, right? We will talk about this more, but it's not going to be black and white that stop the process or don't accept the inference, right? Because what if it's actually a good point for your company? Maybe you need to actually expand to that category, or expand to that basically, I don't know, geography. So you basically create some sort of like a counting, maybe frequency count, something like that, and you see how often this is happening. And if it's something that becomes popular, then you maybe trigger, and this time you use the data for basically retraining, right? So that becomes an idea over here. Is that clear? Yeah. So now, okay, yeah, this is, here we have it. TensorFlow data validation. So it's one of those libraries, basically is pretty good for validating and basically monitoring your data. We will have lab on it, but basically does all of this for you. So you pass your data, it doesn't do it automatically. You just need to stack those. But it gets the statistics, the schema, and gets the statistic and the schemas, and gives you also a function for anomaly detection and stuff like that. And it also gives you the pipeline. So it's pretty good pipeline if you're a TFX user, a TensorFlow user. But let's go here. Okay. So if you look at it from the perspective of TFDV, for alert and analyst, basically it gives you these three options: schema skew, feature skew, distribution skew. Schema skew we talked about is like when the schema doesn't match, like a database schema, for example. And then you have feature skew and you have distribution skew. So the distribution skew, we already talked about the probability of the data doesn't match. Who knows what's feature skew? What could be feature skew? That won't be a skew. A skew means that it's changing, right?
A Boolean variable turns into like three options instead. The way you define the data for that column changes.
The way that you pre-process the data, if you have a pre-processing pipeline, for example, let's say you get categorical and you do one-hot encoding, right? All of a sudden, you do, as part of deployment or something has changed, instead of one-hot encoding, you do categorical encoding, right? So that becomes the feature skew, like, or during the training, let's say, during the training, you found the mean was 10 and the standard deviation was 5. And you use that for normalization, okay? Or scaling of your data. During the serving, you forgot to use this for doing the same thing. So you got the mean and standard deviation from your serving data. Let's say it was something like that. Because you didn't use that. You need to use the same thing from your training data for normalization. So all of a sudden, the features that you have, the range of the values that your features will have will going to be different. That becomes the feature skew. Okay. So now one of the ways that TFDV basically finds the skew, like it detects if it's a skew or not, especially for categorical features, it's L infinite norm. Remember, L infinite norm is basically if you have a vector and you this vector x, if you do L infinite norm, technically is maximum across all values. So if you look at the vector, like it has 10 elements, you pick the one that has maximum as a modular, that L infinite. And if you do L infinite as of between, like as a distance, basically becomes this two vector, let's say the same dimension, okay, becomes across all dimension between these two vectors, like a dimension 1 and 1, dimension 2 and 2. You find the distance between them, and you basically pick the maximum. Okay, so L infinite always returns to the maximum value in the vector or the maximum value in the distances. So that's what TFDV uses for basically detection or skew detection. So if you have two data point, basically it looks at the across all dimension and it returns the maximum. Now, if the maximum value that you detect is more than some threshold, you define some threshold, then that will trigger a warning or some like an email or some counting or something. Okay. So that's the idea in TFDV. The idea behind a schema skew is this: if you were waiting for integer, now you're receiving float. That becomes the schema skew. And again, feature skew we just talked about is that when you types of basic transformation that you applied between training and serving are no longer the same. That becomes the feature skew. And distribution skew, which we already talked about, is when the distribution of the two data, like the joint distribution between training and serving, are no longer valid. Okay, so that becomes the distribution skew. So let's do one thing here. All right, so we're going to quickly talk about weak supervision. Okay. And how we can use that for labeling. It's the main library for weak supervision. It's called Snorkel by Stanford. I think it's a Stanford NLP lab or Stanford AI lab, one of those two. But the idea here is that if you're trying to basically label the data, so let's say. Sorry, the quality is not that good here, but I have data and I want to label it. And instead of basically trying to do a really good job in labeling, I will create smaller tasks which are more noisy from the labeling perspective, but I create series of those. So if I average those, like do aggregation among them, the noise basically hopefully will cancel out, right? So let's say you're trying to basically do a labeling over the data, and the first thing is that you're going to use natural language processing, and you create some sort of like a function that basically gets the data and based on some natural language processing gives you some answer. Second one is that you're basically using some external knowledge-based data sets And based on that, you create some, so you have this subset A, subset B, subset B, like external knowledge. So data goes based on that, you get some answer. The third one is like patterns and dictionaries. Let's say you use regex, for example, searching for certain patterns, and if it matches the answer that you're looking for, and you label the data. Then expert developers is like when you have you pay some expert developers to say, hey, build something like that for this task, for example. Or you use basically organizational resources, you use some third-party modules, like, for example, you have pre-trained model by someone else, or some API calls that you make, and you use that for labeling. Now, you have multiple models. In this case here, we have 6 models that they are going to do the same task. And the idea here is that in the weak supervision is that instead of spending lots of money and time on building a really good labeling system, you spend much less amount of time, much cheaper, building much smaller, basically, or like much noisier set of functions that they do the same task. But the hope here is that when you basically aggregate all of this together, kind of like cancel out that noise. But in order to combine those two, the aggregate, so let's say I just simply look at the output of them as a binary, if it's a labeling, like it's a binary labeling, let's say yes or no. And I look at all the results and I do aggregation, like a majority votes. If like 6 of them out of 6, say 4 of them say cat, 2 say dog, I will pick, for example, to be a cat, right? So something like that. But the better way is that the idea behind this weak supervision was that instead of doing that, we define some weights, okay, for each one of these models, the output of each one of this model, and we learn that through it's like some machine learning model, basically. That's each output is going to be input to a model, and you basically during the learning, at the beginning you have some data, you learn these parameters, right? So it's like imagine you have the output of this output of each one of this, and you're doing a binary labeling, and so you build some logistic regression, right? That gets the output of each models, and each output has a weight, and you already have some labeled data, so you train your model, right? And basically you learn some labels, for example. Yes.
Something like basically you have some labeled data already. You are just judging how good these labelers are and assigning the weights.
So you have some data, you use that data to come up with these functions, and you use that basically to come up with some weights, and then moving forward, anytime new data comes, the new data goes through this, and you get the final output, right? So weak supervision, it makes it pretty fast or easier for development or labeling, development of labeling pipelines, but also, at least based on my experience, it's not every task can be easily break down into much smaller, basically, a smaller subtask, like smaller functions, because you either need to have a really good domain expert on the task that you're working on, or different ways that you can label the data, or it's going to be more challenging, basically. So definitely read this basically document, but there's some, when you work with this Snorkel, which we'll go over, the idea will be you create something called labeling functions. So these are like a different labeling functions that you have, and you label some models and you combine those together technically. That's basically what happens. So each one of these is going to be, these are the 6 functions that we just talked about. To give you different labeling, and you combine them using some classification model based on the weights, and this separation, that's what you end up getting. That becomes the weak supervision. So, all right, so let's just stop on this one. So, now, let's talk about some basic taxonomy, but before doing that, let's understand what's a Docker. Docker is a platform for developing, shipping, and running applications in some sort of like a controlled environment, okay? One of the challenges that you normally have is that it's like whenever we develop a model is that if we want to share it with somebody, it's the environment that we were developing this model or the environment that you need in order to run your model, it's not that straightforward, right? For example, I have worked on a team that we build a model and we use certain TensorFlow, and I think it's like one of those is TensorFlow text. And we are like a Linux user, and TensorFlow text installs on Linux user. It doesn't install on Windows. It doesn't support Windows. So we were working on this model, we built this model and everything, and we give that code to the other team that we have, and they were a Windows user, and they couldn't install the TensorFlow text. So they couldn't work with the model, right? So those are some challenges. Example. Other example is that you built an environment for your code, you have so many dependencies that you have installed and stuff like that. And all of a sudden you want to share that model with somebody and you give a long list of requirements that they need to install. And not everyone wants to go through that process, right? Or not everyone is that savvy to go through that process. Maybe someone just wants to run your model, right? So how could we basically improve that process? Like how could we eliminate the need for all those installation? One of the scenarios is going to be like using something like a Docker. And basically the way that the idea behind Docker is that so you have this like on your computer, you build some app, it's just we call the container app. And you basically what you want to do is that you want to convert that app after your development is done to, and basically it's like some sort of like a standalone version that if I share that version with someone else, if they run it, they don't need to worry about any dependencies or any like, I don't know, like environmental basically variables. So it just makes it easy to run. So there is a container, which is the app itself. From the container, you basically also we have something called images. It's kind of like we will talk about. It's kind of like a blueprint technically, and then there is some sort of like a registry, like a Docker hub, for example, that you can basically dump your Docker files, so anyone else in your company or in the team, like or even public, can access those. Now, idea behind Docker is something like this. Okay, so if you think about so if you think about a machine like here we see the Docker container, what we need basically, you need an infrastructure like a types of machine, whatever that you're running on. That machine need an operating system, like it's a Windows, Linux, or something, right? That becomes the host operating system. And that machine need to have something called Docker engine. Basically, they need to have Docker installed on their machine. Okay, so you need a computer that with some operating system that has Docker installed on it. And if you have that, you can basically share this Docker containers. You have these Docker containers that you're running on that machine. Okay. The benefit of something like this is that if you have multiple Docker container, the only thing you need for every Docker container is the app, which is the code, the main code of whatever your basically has been developed, and some just binary libraries that it's required for running that. Okay. If you have that Docker engine basically, and you have Docker engine installed, you should be able to run that app basically on your machine. In compared to if you, I don't know if you have worked with virtual machine or not, VM on your machine. Every time, if you work with VM and you create a VM, in case you haven't created VM before, just on your machine, do Python 3 -m virtual environment and some name. Okay, whatever name you give, it will create a virtual environment on your machine, right? But if you do that, you will see that the size of every virtual environment is about 4 gigabytes almost, right? So every time you create one virtual environment for a project, that takes about 4 gigabytes of your hard drive. They are pretty heavy. Why? Because the VM, every time you create a VM, it actually creates its own operating system, like a lightweight operating system. So this orange will be part of that VM that you create. So if you create 5 VM on your machine, 20 gigabytes gone. If you work with Docker, we no longer do that. We don't need to recreate the operating system. I'm using your machine operating system, and the Docker engine basically does the job. Okay, so that was the idea. Like VM is pretty expensive when it comes to that. Now, overall, if you look at the Dockers, basically, you have Docker file, you have Docker image, and then you have Docker container. So let's start with the right. Docker container are lightweight, standalone, and executable package. It's a package that you can basically run it. That becomes the container. You normally have something called a Docker file, which is your piece of software, basically. That's your Docker file. We will see how we can write this. Inside of Docker file, you have information like, it's kind of like information like what is necessary to build a certain image. What is, for example, the version that you are using? What's the source of data? What's, I don't know, what you're going to run. That becomes Docker file. When you have a Docker file and using Docker command, you convert that Docker file using a command called build, Docker build, into something called Docker image. Okay. So Docker image becomes now, so the Docker file, you build it into an image. Okay. Now, image is technically, think about it, is an immutable, like a blueprint. I have this application built into a blueprint. Now, if I want to run it, I can run it using Docker run. And when you run it, that converts it to a Docker basically container. Or maybe I don't want to run it and I want to share it with somebody else. So you share that Docker image. So that becomes the overall idea. So you have a Docker file, which we will see how to create today. You can basically build it into a Docker image. Now you can do 2 things with Docker image. Either push it to the repository, either Docker Hub, it could be like a private company repository, or you convert the image into the container or the application basically. So you can basically run it technically or work with it. So there are 2 basically scenarios that could happen. If you push the Docker image to Docker Hub, someone else can pull it and then they can do the same thing. Is that clear? All right, so. And all right, that would be summary. So let's do. In the repo, there are 2 labs for the Docker. Okay, so I'm going to start with lab 1, and inside the lab 1 on the folder, as you see, there is a folder called SRC where the main code is going to be. So in SRC, I have this main file. It's just a random code, basically. Just get some data from what's called scikit-learn and ran the job, basically trains a classifier and save it, and at the end just says that print the model training was successful. Okay. In order to run this piece of software, you need some libraries. You need like a scikit-learn and you need joblib. Okay. Now, let's say our goal is that to have this piece of code somehow containerized, so anyone else can run it without a need to go install scikit-learn and joblib and stuff like that. You just give it to somebody else and they should just be able to run it. So first thing we do, we create this here, this requirement.txt, and we just put the name of the 2 libraries that you need for the code. We close that. And then I go 1 subfolder before SRC, and you create on your machine a file called Docker file, lowercase, okay? So inside the Docker file, the command that we are using, so always on top, it starts with, okay, what do you need to run this? What's the language you're running? So we are going to say we're getting Python 3.9. So you always start with from, it's always like uppercase letters. From the version of the Python that, for example, you're using. Then The next step is that, so you need to set the working directory. Like what's the working directory for this basically application? So basically here we say working directory is called app. App doesn't exist. You're building that app as part of your Docker. Okay. So you create a working directory called app. The next thing is that you need to copy whatever code you have, you want to be part of that working directory. So basically you say, copy the folder src in, that means that in the current folder, which becomes that in the app, right? So you copy this folder on the left, src, into that basically container. Is that clear so far? Then, what do we need in order to run the code? We first need to install those pip dependencies. So you run, basically run again uppercase, pip install that requirement.txt. Okay, so this is really similar to what you saw in Git Actions, a step-by-step task to be done. Last is like, okay, we have installed all the dependency. Now I want to run that code. So basically you use command line, you use cmd, and I want as part of cmd to run Python main.py. Okay. So this is cmd means it's a command line, and that command line starts with the Python, and after that comes main.py, which main.py is in the src. Okay. So we copied everything from the src folder to the container, which is one of them is requirement.txt, one of them is main.py. We use the requirement.txt to install the pip dependencies, and we just ran the Python. So we put that all in one file, and we call it Docker file. And when you do that, and also use this language, if you have Docker installed on your machine, it automatically detects it as a Docker file. So that, like, for example, on SVC, it automatically finds detects it as a Docker file and gives us some icon to it. So now, if we want to test this out, okay? So I have Docker installed. So I want to first convert that Docker, basically Docker file into an image, and then you can either push the image or you can run the image technique, convert it to a container. So you do Docker build -t, and then we want to give it a name. So let's say app version 1, okay? And you put a dot. So you're basically saying that to build from this, so when you run the Docker command in the folder, it automatically, because it detects that Docker file, right? So I say that dot means like anything that's here. So I basically say that and this app and v1, what does that mean? App is a name that I pick, and v1 is a version that you pick. Basically, you can change those. So here, if you do this, it starts converting that Docker file into a Docker image. Yes.
-t for
Tag.
tag.
Yeah. So -t is tag. We're going to see that more of that now. So it takes a while. Unfortunately, it just takes a while to run. And after this ran and is finished, if you do on your machine Docker images, Docker space images, it gives you a list of all the images that are on your machine. Okay. So look what's happened. As part of the image, it does all the installations. Right? So user didn't need to do any of those. It's like you built this script blueprint that does all the tasks for you. So you don't need to do user step by step, basically to do the installation, run the code. Just all you need to do is just to give them that image, you know? So this is an image now, right? And the user doesn't need to even to do that. I have an image, I'm going to push the image, you get the image. So you just need to run the image technically. So if I do here, Docker images, it tells me that you create an image. There's one image in my machine local repository called app version 1. This is an image ID. It was created, and this is the size of the image. It's not, the Docker is also, they're not small, you know, it's kind of because it takes all those dependencies installed, right? Now, if I want to run this, Docker run, basically V1, version 1, because you might have different versions. And the model training was successful. So it automatically ran the code, you know, and done. Is that clear? So that's just a simple scenario of building a Docker. Now, let's take that to another example. So one thing I also always do is that I have this script that I just run it to get rid of any, so Docker, the problem is that if you keep adding Docker, also takes the space, right? So I basically run a script that cleans all the Docker images and Docker, basically background Dockers that I have, and so it doesn't make my computer slow. It's a good practice to do. So let's go to lab 2. And now we want to do things a bit more interesting. Now the idea in lab 2 is that we want to build the, let's go to model training. So we want to build a model, okay? And I think if I'm not wrong, the data set is the iris. Yeah, so you know the iris data set for the 3 types of flowers? Yes.
Don't mind, can you show the program which you're running to clean up the Docker?
So it's I don't know how to zoom in. I can't zoom in, but basically it does some Docker stuff and remove that, basically gets rid of the volume and network connect. Because Docker can easily attach to your network, your basically drive and stuff like that. So it's, over time, I have had issues that all of a sudden I'm like, why my computer is so slow? I looked and I had like about like a 40 gigabytes of Docker just in the background. So it's good just always to run it when you're done. So now, you know the iris dataset, right? So it's basically there are 3 plans. So the goal here is that we build a classification. Then we want to build an basically Flask API. Okay, so how many of you haven't worked with API before? Like a Flask API, Fast API, stuff like that. Don't be shy if you just raise your hand. So I want to know. How many of you don't have a knowledge on APIs? All right. If you be shy, then I would like, I'm like everyone knows, so I don't need to teach it. Okay, so, all right. So we will have full labs on APIs coming, but the main, think of it like this. So what we want to do, we want to create some sort of like an application interface, basically, okay, that whenever you have, let's say I'm running this code and I want to serve this code to users that, so user can basically go, I have a classification model and I want the user to be able to go give data to this model and get the result. So I want to build some sort of like an interface, application interface, right? So that's the idea here. One of the ways that we can do, we can use with something called Flask. It's like one of the cool library, like a Python packages, Flask API. So install Flask on your machine, then from Flask we import Flask itself for the main class, request, JSONify, render template. So request is for, you know, when you're creating a request, like sending a request, getting an answer, like a requesting. And JSONify is whatever data you get, you want to convert it to a JSON. JSONify, it just converts the data to the JSON. And there's the one that I'm using, render template, is what I will do is that instead of, so I want to build some HTML, like a page, and I want this Flask API, when it comes up, to use the whatever templates that I have as a page for my API. Okay, I'm going to show you what's that. But in order to do that, so this render template is a function. So you build some HTMLs and you just say render that for me as a template to build the API. Okay. So the first thing you do, basically after you did all the import, you need to create something called like a Flask API instance. So here we call it an app. You can call it again whatever you want, but you call it a Flask, like the main class, and you say that basically underline name, that becomes the main Flask that you have here. Here I use something called a static folder. It's because as part of that templating, basically using that HTML, I have some images that I want. So this is the idea. When user make a prediction and the image is, for example, versicolor, instead of just saying versicolor, I want to show an image of a versicolor, right? So what I have done, I put 3 images in a folder called statics, okay? That folder's one for versicolor, one for, and what was the other ones? Virginica, and the other one was? I can't see it. Oh, yeah. Okay, so I have 3 images basically in a folder called statics, but in order to tell to Flask API where's the source of basically these images, you use this something called a static folder as a parameter, and you pass the address to that folder. Okay, so that's the idea behind that static folder. Now, the next thing is that we are going to create some sort of like this is like a URI basically for the address. This address 4000-predict becomes the address for accessing the model for making a prediction. Okay. Now, step 1, we load the model that was trained before. We haven't trained it yet, so the idea becomes that the Docker image that we're going to build is going to have multiple steps. Similar again to Git actions. Remember we had those steps. Step 1 works on model training and saves the model. And the second part works on serving the model. Okay, so that's what we want to do. So we need to load the model. This is assuming that the model was trained first. We load the model, we come up with the class labels. Then this app, this basically app that we have, we want to add addresses to. This is like a API, right? So you add addresses like a website, for example, as just an example. So here, basically what we do, you create a function, basically like we call it home. We decorate that function with this address. We basically say that this function is decorated. It belongs to that app, and this is a root home. So if you put .root, basically backslash, that means main page. Okay, so this function belongs to the main page of the app API. So if you go to the main page of the API, I want you to show this message. That's what basically we are saying. Is that clear? So if you think about when you go on any website, basically, so you have always this backslash and address, right? So that's the same story. So we're basically creating a main page because there's nothing here, main page, home page. If user goes to the home page, this by default, that learns that because I'm on the home page, I need to show this. You make them as like a functions, basically. The next thing is that, okay, I want another page, another address, but for prediction. What if user wants to work with the model? So you create another function. Here we call it predict. And again, the naming is just conventional. You just select whatever name you want. Predict, but this function, you need to also decorate it. So we say app.basically route, what's the address? It's going to be backslash predict. So this is if user goes to main page with backslash predict, this should be triggered. Okay, but then there are two basic things to keep in mind. When you want to make a predict, what is the type of connection that you want to make with the user, right? So here, the methods are basically what's the methods of the types of connections. So one is that to get data from user. The other one is that to post the answer to the user, right? So get becomes for the part that you let user to pass the data, and post becomes as a method to passing back the answer to the user. So you say that this function is going to, again, be decorated and has 2 methods. Is that clear? So now we test. If the request.method is post, that means you are basically giving the answer, you're posting it, right? So from the request, basically, we get this information. We have the data. So data comes from request.form. it's for that, if you think about that data set has only 4 columns, like a sepal length, sepal width, petal length, petal width. So you, from the data, you get those 4 information. You assume user has entered that because it's a post. Okay. So you get those 4, you put it in a variable, you put it in an array and you pass it to the model. Model makes a prediction and you pass that prediction to a label and you get the label for that prediction. Okay, so this line. Then we want to convert that answer into JSONify so you can basically present it to the user. All right, so we convert it to some JSON format. How JSONify predict class equal this. All right, so that's how we use that JSON. And if there was exception, basically you put some, you return some error. Then if the method is get, basically we basically say that to render from this template that we are talking about. So there are some templates that I'm going to show. If the method is get, to basically render that template. Now, else basically we say that this whatever method that we are receiving is not supported. Is that clear? So then we basically, you need to run that API, and you run that API this way. App was the name of the API that you created, .run, and we basically run it, and you could set that debugging for it, debugging through. What's the IP do you want this app to run? This IP, and this is the port basically. Okay, so you create this file. It's file for the API. Okay. Now we want to, so we have that. I'm going to talk about this templates later. So these are in the SRC folder. We want a Docker file for that. Okay. So let's go to the Docker file. So we start the same thing here. There's only one difference is that I want my Docker file to have 2 parts. One was for the training, one was for the serving. So we basically start same thing from Python 3. For example, version 3.9. And here I say that as model training because I want to, maybe I want 2 different versions. So I said this one is for model training part. You copy, basically you create a working directory, you copy whatever you need into that working directory. You copy that file for requirement.txt and you install those whatever pip you need. After that, you just run Python model training. So this runs the first script, which was for training a model and saving a model. Or creating a model. So then you go to the second part. The second part, we basically get another basically from Python things as serving. You create a basically working directory. However, in order to run the second part, which is the API, you need the model that was trained before, correct? So one of the things I will do is that I will copy from the other environment model training above, this address, this model file into the app, which belongs to the serving. Because right now we are inside this from, say, serving. So you have 2 separate environments, all right? So we get the model training, sorry, from model training, which again, if you go up here, you see this is the model training. So from here, that is all model training environment. Inside that, basically, there is a model file after we trained it. So we want to pick that and add it to the second part, which is here, to whatever that comes here. Okay. So here, this copy basically does that. Then because we now have the model file, then we copy main.py, which was the code that we just went over for Flask API. We copy it here also. So far we're just copying files into this basically Docker file. Then we need to, because we want to serve the API, and in order to want to serve the API in a Docker, and you want it to be accessible to someone outside of the Docker, basically, outside the Docker environment, you need to expose a port. So here what we do, we basically expose the port 80, so it becomes available. Then here, basically, what we do, I want to serve that basically Docker, basically, or sorry, serve that Flask API. We create some environmental variable. We copy that requirement.txt. We install whatever package that is necessary to run it. We copy this template folder. I'm going to go over that template folder, but that's just HTML files that I was talking about. So we copy those template folders also inside the basically Docker. And then we also copy this statics. That's the images of the 3 flowers. And at the end, we just run main.py. So this has 2 parts again, 1 part for model training, 1 part for the serving. Is that clear? So let's go here now. So in SRC, statics has 3 images only, nothing else. Then there's this template, predict.html. So this template, yes.
So does it mean it run to 2 different containers, like one for model training and one for this? Or-
No, the statics was only part of the serving part. I didn't copy it. So if you go to, let me see if I copied. So inside the first one, I only copied model training.app. I didn't copy anything else for the model training. For model serving, I copied the statics and I copied the templates and the main.py.
So my question is, are they like 2 different containers, only one container?
So here, basically, we have 1 container, 2 environments. Right? Yes.
You use trusted host for stage 2, but not stage 1. Any particular reason?
Yeah, Keras, TensorFlow, sorry. I think if that's the case, or Flask. Sometimes some of the libraries are not easy to find. Docker doesn't find them. So if you use this trusted host, basically, if you try it, you will see that it basically tells you that unknown host. It doesn't install some of the packages. So when you do that, it's kind of make a trusted connection. So it allows you to install this.
Because I noticed that you're using 2 different ports. One is at port 80 and one is at 4000.
4000 is the port of the app. 80 is the port that Docker's exposes.
The difference.
So app runs by itself. It runs on a port, for example, 4000. Docker, but it runs inside the Docker, right? So it's basically closed to outside. So Docker says that, okay, I'm going to expose a port that everyone can access that.
So it's not directly accessible to the user.
That's correct. So without it is exposed, you won't directly access that. So now this template, it's ignore it. It's just an HTML file. Okay. It basically none of this matters. It's just colorful. Basically, try to put some colors on the page. The main part starts from here. So here to here. So when user goes to basically when the user makes a post, okay, so the post basically, get, the get basically renders this page, and this page and on the top shows something like that, and it basically gives you 4 boxes to enter information, enter the number, what you want to make a classification. Tells you what's the sepal length, what's the width, petal length, petal width. Your user so enters 4 boxes. And after that, it makes a classification. It gets the out with this classification. But the idea was that when you get the classification, it compares the classification with that folder, statics, and map it to the correct image. So if it was Satursa, basically says, show this. If it was versicolor, show this image. If it was vertical, show this image. Right? So you don't need to focus on this. I didn't even write this myself. It's like literally this comes out of a GPT model. So it's like, give me HTML with 4 boxes. That's that to that level. You want to learn it, read it is pretty straightforward, but I didn't even write it. So, and here basically this just additional some. I needed to do some of this because the images were not showing. So there's some additional information. So it's overall this is HTML for doing that. Okay. So now let's do one thing. So let's pick this. So we want to do the same thing. So Docker build -t, and let's call it app again, v1. Sorry. There's a dot at the end. So you do the same thing. You convert the Docker file into a Docker image. And Docker image could be shared, could be run, and we run the Docker image. What we expect to happen here is that when we, after building, when we run the Docker image, which becomes a Docker container, inside the container, two things should have happened. A model should have been trained and created, and that model should have copied to another environment and then was served as part of the Flask API. And we should be able to access that Flask API, basically, okay? So, while we're waiting for that, any question on those? All right. We're going to finish it and we can take a break and then we continue. Also, not that necessarily you needed to have two separate environments for serving and training, just as an example that show you can have those separate. You know, otherwise we didn't need to wait this many time to install TensorFlow. Just a practice here. It's the. Almost done. All right, so let's look at something. Docker. Again, the size this time is much larger because we have more libraries installed. Also, we have a larger model basically, but now we want to basically serve this. So when we do this, and it's being served. So the first thing you will see here is that this IP being basically available now. So I go here, basically says that on top small, but welcome to our basically classifier. So if I go to this is the home, that's the home address, right? If I go to predict, then basically this page comes up and you pass, I don't know, something like that. And basically makes the prediction, right? So that becomes the whole idea. It's like, now, think about it. User don't need to know what happened. They don't need to build this. All I need is to share that Docker image. And all you need to, user there is basically to run the image, right? So it's kind of, they don't need to know all this dependency, installation, environment, everything that goes through it, right? Okay, so let's take a break and then we continue from there. It's better to finish it in a week or so. It's straightforward. It just has like each worksheet, I think has like 8 questions, like some of them are like literally tick. Have you thought of it and not something?
Do we need to answer all the 12 points? Like there's a file structure, we aren't sure of the file structure.
Just put some rough estimate. Again, you can change it as you go.
It's not final.
No, you can, scoping, you can change as you go through the semester.
So a lot of changes, we are assuming a lot of things.
But it's important to remember that some stuff as part of the scoping shouldn't change that. Like file structure, yes, but the goal of the project, you can change it if you see like it doesn't work, but it should be like a pretty defined at the beginning. All right. So we're going to start with airflow. It's think about airflow. It's basically a tool or library created by Apache. Called Apache Airflow. It's an open source platform for developing, schedule, and monitoring basically batch types of jobs. Okay. The idea behind Airflow is that it's just kind of like a workflow as a code. So you want, let's say I want to schedule. I have a code that does certain tasks. Let's talk about just simple data pre-processing. And my tasks are that I will basically download the data and I do some cleaning and I do normalization and I do feature engineering and so on. I have this basic task that I want to do. Either they are sequential basically, or there could be some in parallel also. And your goal is that how could I orchestrate this task? How could I ensure that everything runs in the proper order? And if something didn't run, I get basically notified, or if everything went fine, I also could get a notification or something like that. That way, you don't need to manually trigger and run jobs or stuff like that. Basically, you have this orchestration tool that monitors that for you and also gives you an update, on that. So one of the really popular tools is like called Airflow. And the idea of Airflow is that in order to connect these tasks that you have into some sequential, basically, like some executable, basically task, what you want to do, you want to convert them to something called a DAG, directed acyclic graph. Okay. So the idea behind DAG is that it's a graph, so it should be directed also. Acyclic means that it shouldn't have any cycle. Basically, just everything is just one way. And the idea would be that all you need to do is that first create an empty canvas. Think about like that. I will start with an empty canvas and call it a DAG. Then you pick one task at a time, depending on the order that you have. And each task becomes a node as part of that graph that you're building, and you add it to that canvas. So I will first pick this one and I add it here. Then I say after this will run, so I will add it here and make a connection like that. And so on. Maybe sometimes you have this. And so on. This becomes a DAG. Directly assigned here. It shouldn't have any basically circle like that. Okay, that's important. It's not that it's impossible, but it's not you won't see it. Maybe someone does it because the task is difficult, or challenging, but normally you don't have something like that. Now, the way that basically you work with basically this or create a DAG is that it always basically after doing some imports, we're going to talk about the imports more in details, but you basically need to create a canvas, and inside the canvas you need to create these dependencies. Okay. We're going to go over the code right now. So the dashboard it will gives you is something like this. So here basically says that there is two operations basically happen. So this one happened. The green means happened. The red basically means failed or something like that. The color codes are added here. So yeah, red is failed. Then it also gives you a view like this that over time what happened to the task, and the length of the bar says how long it takes to that task to execute. If it's basically dark green means it's executed, finished, successful. It's basically bright green means it's running right now. It's like running in the background, for example. Now, so let's get away from that. Let's go to our lab. So we have these folders in the repo Airflow labs. We're going to start with lab 1. Now, in order to work with Airflow, in the folder so here what I do, so you have two ways. So we have also, I think, two ways. We have videos for all of those approaches. You can either install Airflow on your machine, like a Windows, Linux, like as an installer, which we have videos for those. Or you can use Docker basically Compose, Docker version of the Airflow. So you don't need to install all the dependencies. We found out every semester students have hard time with installing on the machine, some dependencies issues, some network, like a network basically properties doesn't come up or doesn't work. So to make it easier, we're going to just work with Docker Compose, which is released by the Airflow itself. Okay. So the first thing you need to do is that whatever folder is that you're trying to run Airflow in it, in that folder, you need to first have a folder, subfolder, it's called DAGs. Okay. And that's where you're going to have your DAG over there. So you need to have that DAGs folder, okay? So we have this DAGs folder. Inside the DAGs folder, we have whatever we need. Like I need data, I need SRC for code and stuff like that. So I have this data files. Then inside the SRC, I have a code. So there's this lab.py. So which again is just, we're going to see this non-important, but what it does. So this file, this Python file has multiple functions, which are going to be these functions. Okay. So inside this lab.py, there's a function for loading the data, which returns the load data, doesn't have any input. There's a data pre-processing, gets an input. So I can actually call this. So data pre-processing, so the output of this goes to input of this. Okay, output of this goes as an input to this. Then we have build and save of model. So let's say this is build and save. So the output of this plus output input by a user, like a name of the model, goes to this one. And it basically build and save a model. So this one, what it does, it saves a model and it returns you and something. It returns you an SSE. Then we have the other function, load the model, which is a separate model. If it gets a separate function, if it gets a model name, it will load the model and makes a prediction. It returns a prediction. So these are like separate functions, like it's just, okay. So what we want to do we basically want to orchestrate this in a proper way to run, okay? And we want to basically be sure that someone can basically manage that orchestration. Now, so this model folder is just whenever you run it, that will create automatically that model folder for you. Now, so the other folders that you see here, config, logs, plugins, and working data, those are folders that Airflow will work with automatically, okay? So the only thing right now we have is technically, the only thing we need is this DAG folders, which had the code we just saw, and this Docker Compose file, which again, this Docker Compose file is on our GitHub, but it directly downloaded from their website, okay? So what's a Docker Compose? So you, in the previous part of the lab, you saw Docker file and Docker images. It's when you have one application. Docker Compose is when you have multiple applications that they want to run together. So instead of having a Docker image, you basically end up with a Docker Compose. It's a compose of multiple, basically, images, so multiple applications. Okay, so in this Docker Compose, basically, again, we don't need to understand the details. Even I just read some of this, it's just provided you can use it. But overall, it starts with here. It says that this is the image. It's going to get Airflow, this version. And it needs some environmental variables. So it's by default is in the Docker Compose file, okay? But, so there are some of this, they are default, you don't need to change. There's one of them, for example, is this one, Airflow core load examples. By default is on true, set it to false, because what it does, it loads lots of examples. So when you open your dashboard, it's full of examples. It's hard to navigate through. So just always set that to false. And the rest you don't need to change up to here. Pip additional requirement. That basically tells you that when you want to run whatever functions that you have, what pip functions do you need to, it's like something similar to the requirement.txt. You're going to list basically the libraries that you need. Okay, so I need basically this to have. Okay, so name of the pips that you have. And the rest of this basically leave the same. As you go down, and you see this IP, these ports, they all leave the same default. They work always with the same IP and port. And there is a part here for password, somewhere here. Here. So if you want to basically have a password for your Airflow so no one can access it, you can basically define a username and password here. So when the dashboard comes up, only if you have this username and password can log in. Okay. So, all right. So all right, that's it. So let's close that. And again, the Docker Compose comes provided by Airflow, so you don't need to be really worried about it. You need to be able to adjust it based on some requirement. Maybe you need your task cast. But at first, just try to just work with it the way that it is. So, because it's a Docker Compose, so what we do, basically say Docker Compose Airflow init. Compose. Let me see, Docker Compose Airflow init or Compose Airflow.
Compose of service type connected. Airflow service is initialized connected.
So yeah, okay. There's a dash here. All right, Docker Compose of Airflow dash init. So you first, this is similar to the idea of like when you did the Docker build, like you converted the file to the image, we do the same thing, then we run it basically. So now, as part of Docker Compose, there are multiple basically applications that are going to run as in order for the Airflow to run on your machine. So if I go here to Docker Compose and just scroll down, what we will see here is that there is this Airflow init. We just saw that. Let's go Airflow worker and Airflow scheduler. So when we do this Docker Compose basically up init, and then after that, if I go get list of all the Docker images on my machine, we will see multiple Docker image, not one, because that Docker Compose is composed of multiple basic images, right? So unfortunately, it takes a little time to basically run, but let's see if we can already do that. Yeah, so you see, it's already actually created Postgres, Reddit, Apache Airflow, like different images on my machine, basically, right? So, and that's basically what it's written as part of the structure in the Docker Compose file. So, okay, let's see this one. Okay, this one is done. So now if we have that, so basically you just say Docker Compose up. Now it brings it up basically. So it's going to take, unfortunately, again, some time to come up, but let's see. So if we do Docker PS, so these are all the applications that you see, containers that are right now running, basically because of this Docker Airflow. So we have Airflow 2, and then we, maybe I need to zoom out a bit. So that way is better, but I know you cannot see it, but technically, so these are the names: Airflow Trigger, Airflow Web Server, Airflow Worker, Airflow Scheduler, Redis, and Postgres. So 6 containers are running on my machine as Docker. Now think about how easy the process was. If we didn't use Docker, you need to install a lot, right? Take care of all this dependency. We use Docker Compose. We just need to basically build it, run it, and you have all these containers running on your machine, right? So, and then it also tells you about the IP and ports that there are, types of connections that each one of those has. So if I go back here now, and this one is running, so it's running here, listening at this port. So if I go to this address, so this is the main page. Everyone see this? So this is the main page, and you see here on the left, because it connects, it already searches in the folder for the DAGs file. So it already found a DAG file. But where is this DAG file coming from? So we haven't seen that, right? We only saw a source code. So let's go back here. And we go to the DAGs. There's this airflow.py. The name could be anything. I just call it airflow.py, right? So that is the DAG file. So let's go inside that. So we're going to see how to create a DAG. So we basically start by importing, you saw right now in the previous lab, we did from Flask, import the main class Flask. So here basically you do from Airflow, import the main class here, DAG. So that's the empty canvas that we are going to talk about. That's this canvas basically. So you import the DAG, then, so Airflow is actually one of the cool things about Airflow is that it actually has connector for almost every platform or whatever you want to run on. So if you want to run a Python code, you have an operator for Python. If you want to run a Java code, C++ or Bash code, you have an operator for all of those. If you want to run a code on GCP, has an operator for that. It connects to almost everything. Okay, so it's pretty useful. So we want to run a Python code. That means so think about this. One thing about Airflow is that Airflow itself is just a scheduler. It's not a compute machine. It doesn't have compute engine. It uses your machine compute power, and it just schedules tasks for you. So it's kind of like a middleman, right? It's just it has the time sheets and it says, okay, at this time I'm going to call to this function, it's your turn to run. Then I'm going to call to this one and so on. So in order to make those calls, you basically tell to the Airflow that, hey, I need you to run these functions using Python, okay? Or I want to run it using Java, Bash. So it needs, because again, itself doesn't have that knowledge. It needs somehow, technically, it needs a Python to run it for you. So basically you say, from Airflow.operators, they have list of operators, .python operator, import Python operator. Basically, it's just a function operator to run Python codes, basically. So I highly recommend you go to airflow.operators, see lists of all the possible connections that the operators you can get from Airflow. So then we get something for time delta, and then we import all these functions that we saw in all these functions, we import it in this file. And then Airflow basically import configuration. It's like you can also set pre-default configuration at the top of your Airflow. And you can basically do that by importing that configuration file. Then, does it make sense so far? So then we start with this line. So this one basically configuration set, I want to enable XCOM pickling. What's XCOM pickling here is that I want to be able to pass data between different tasks. And in order to be able to do that, you need to enable this XCOM pickling, basically, okay? So that allows you, again, to pass the data between tasks. So now, so up to that point, we just did the import. Then here, we're going to basically create a default argument to make it easier for us. So here, for example, as an owner, you put your name, start date, you set the start date or define a date for the whatever you want. Retries is that means if the task failed, how many times should I retry? And retry delay if you want to retry so where should I get those keys? Like just look at on the Airflow's list of keys and just you will find out every possible keys that you can use for this default configuration, right? That's not the important one. So now we're going to start. What do we need first? An empty canvas, right? So you start by creating a DAG and you save it as a DAG also. So we say that this DAG, you need to basically give it a name. What's the name of this DAG? Because remember in the dashboard, you need to be able to see the names. So you give the DAG a name. Then if there's any default argument, you pass it to it. You give it some description because sometimes you have series of these. So you want to be sure there's some description short. If there isn't a schedule interval, that means if you want it to be some job that runs on schedule, you basically set that. Otherwise, you just none. None means it becomes a manual trigger, for example. And if you want it to catch up or not, like if you want basically to have some sort of memory, I'd say, no, I don't need. Okay, so you create this here, we create this canvas tag. Yes. Like some cache memory, basically. Yeah. So then we want to go over this. You have 4 functions imported, but those are Python function. So what you need to do, you need to wrap those functions in that Python operator that we imported. So basically what we do, for every functions that we have in order, we're going to call to this Python operator. Why in order? Because we just talked about this. Sometimes you want to remember the dependencies. So start with load data. This doesn't have any input. It's just a function you call and it gives you an output. So Python operator, you give it some task ID. And what's the Python function you're going to call to? This load data. And what is the DAG you are connecting this to? The main DAG. Simple as that. So you create an operator to call to a function and is attached to our canvas, like our DAG. Then we go to the second function. Second function, is still Python, but it gets the input from the previous one. So Python operator, you give it some task ID. What was the Python function that you're calling to? What is the operational argument that it received? We will say that this one receives the output from this one. Right? Straightforward. The output from the previous one. And you connect it to the same DAG. Then you go to the third function. Give it a name, and it has two inputs, the output from the previous one and a name that you pass to it. So it gets two operational arguments, the output from the previous one and a name. Connected to a DAG, right? So provide context also, is just, if you wanted to give more details information, you set the provide context to true, right? Then the last one, which is the load the model, basically does the same thing, gets the output from the previous one, a model name, and connected to a DAG. So we create a four basically operator, function operator, like a Python operator, connected to the DAG. But there is no sequence defined yet. Okay, so we just defined this, we haven't sequenced them. So in order to sequence them, that's basically you define the dependencies using it it's like a chain rule, basically, right? First, we run this, then it run this, then it run this, and then it run this. That defines the dependencies, basically. I don't know if you work with R, that's a function similar to what we have in R. And then you want to basically this code to run. So when you create this DAG file, a file that basically is basically a DAG, and you run your dashboard, it automatically detects that. You run, your Airflow, it automatically detects that DAG. Basically, it says this is a DAG. So if you click on the DAG, it basically gives you all of this, like how many times you run, success or fail. If you click on here, it says graph. So details gives you the details, as you see. I'll let you to go through it yourself. If you go on graph, shows the dependencies that we just created. You can go on individual one, and you can go to code. You can go Gantt. You can go to logs. All right. So it basically gives you all those information. Task duration, which we're going to talk about that in probably next lab, with more details on how to use information like that to maybe optimize your pipeline, to find the bottlenecks and stuff like that. And so overall, it's like some color coding for information. If you want to do some like a search, you can basically do something like that. If you want to filter, you can use that filter. If you want to go to cluster activity, my machine only has one node, basically I run it as one node, but if you have actual clusters, so you can see information about every clusters. Here, for example, it says that my cluster is healthy, scheduler, so you have three main things: the database, scheduler, trigger, right? It says all three are healthy. You always want that to be sure that they are healthy. And there's some statistic information here. So if you have data set, basically it will show it. I don't have anything. Security, you can basically set users, assign rules, who can access what, who can control what, basically. Resource access permissions, you can define all of those. Have the browse here. Admin, there is on top this variable. Similar to what you saw in GitHub when you have a secret variables or some environmental variables, you can define them here. So you don't need to pass those to the model. Okay? So now if we pick this, so you have this Airflow, and if all I need to do in order to make it run, click trigger DAG, if it's a manual process. So I say create trigger DAG. If I go here, you see this is running. So if I go to graph mode, dark green means done. So this one is right now running. If it's finished, it goes to the next one and says all for example, finished, right? So this becomes a scheduler, and this example, we have it on a manual trigger. Next example, we're going to make it automate trigger, or give it more branches, basically. Any question on that? So, all right, so Now let's do one thing. So I'm going to close this. I'm going to stop it. So let's go to lab 2. Now, idea is the same thing. Now we want to do, we want to just add a little details to this. So let's say you are building an application, and your goal is that or let's just say you have a pipeline. Actually, in this example here, so we have a pipeline, and this pipeline every day I need to run and train a new model for me. Okay? This pipeline needs to run automatically every day, goes through a series of steps, develop a new model. So whatever is this DAG, whenever it is run, it gives me a new model. Okay? But I don't want to manually go check this every day. Say, hey, is it like, did it work or not, right? Or did everything went well or something went wrong, you know? So instead of doing that, what I want to do is that I want to have another DAG 2. Because DAG are independent of each other, right? But I want to have another DAG that listens to this DAG. Okay? And basically listens, or you can actually have it the other way around. This DAG to make a call to this one. Whenever it's done, I want this DAG that finished the model, developed the model, to make a call to this DAG, says I'm done. Or this DAG is listening and says that, hey, let me know when you're done. And when it's done, if this one was done, like a successful, I want this to run this DAG. But also, I want to receive an email or a Slack message that run was successful or run was failed. But also, I want this DAG to, so let's say I'll go to work and I'm like, I have a couple of ways. I can either manually go check to see that everything works, or maybe I want to create an API that all I need to do, maybe from home, just go to this address, and that API gives me some statistics and some information like, yeah, run was successful, everything looks good and stuff like that. Instead of me working with Airflow, I just go to an address API. Does that make sense? So that's what we're going to do now. We're going to basically build this one. So it's going to be this part. It's going to be this part that works on an API, basically API only if this was successful, basically give you a success. Otherwise, it tells me that it was a failure. So pages will change basically. Okay. And then I also will receive an email, you know. So in case I need to basically go check check to see if something is wrong. So in order to do that, so first, again, you need a Docker Compose, the same thing. However, there is a little difference, and the difference here is that in order for the Airflow to send me an email or send you an basically some sort of like a notification, especially as an email, and I'm using Gmail, you need to give Airflow some permission. Because technically what it does, it uses your own email to send you an email. Okay? So it needs to have access to your email. So you need to have some SMTP, basically password and protocol, basically. You need to set some SMTP password. How you can do that on your Gmail, if you just search on Gmail, SMTP, basically app password, there's a page, actually the link to that is also on the GitHub. You go to your own Google Gmail, and after you log in, it tells you like, I want to, it's basically the page comes up, you give it a name, like a key, basically, private key. It gives you a 16-digit password. And all you need to do is that you need to basically bring that 16-digit password and add it here. Okay, so you add your email and you basically add that 16-digit password. So that password is for program applications to authenticate themselves with with Google, basically. Okay? So, and of course, after the class, get rid of it because now everyone has that password. So, so that's the only change in the Docker Compose right now. The same Docker Compose, I just added this SMTP section. It's by default wasn't there. This part, it was not there. So you also have the updated, basically Docker Compose for this lab. Now, let's go back to the DAGs. So we go to the DAGs folder and start with the SRC. So the model and data, ignore it. It's just a model will save their data as a data for. So model development is exactly the same thing that we saw in the previous lab. To just go through a series of processes and save a model. Okay, so nothing has changed here. So I'm going to close that. Then I have this Flask API, which is for the API that I just talked about. And the idea of the API is that, so wait, we put this on the DAG. Yeah, okay. So let's come back to the API after the other. So let's go to the main, the first DAG. So there's a bunch of imports that I'm doing. And again, lots of things that you see in these labs are not that necessarily the best thing. It's just to show you how you can alter between different things or just practical. So we have Python operator, and this time also I'm using bash operator. You see there are two operators to just show you that how you can switch between different operators. So we import all the files and they import the configuration file. And then we are, for the email, you need email operator. From Airflow, operator, email, email operator. Right? So everything is just that you need some sort of like operator it has. Now, we need two other things. Airflow operators trigger DAG run operator. What's that? It's I need an operator that does this task. Trigger another DAG. Okay? So when this DAG, the current DAG, is done, if it was successful, I wanted to make a call to another DAG and trigger that DAG. Hey, run, it's your turn. So in order to do that, we basically import this one, trigger DAG run operator. Okay? And again, best thing is that just go on the list of the operators. You will find a lot basically to work with. Then trigger rule. So here, you see this sign, I said only trigger if it was successful. So I want to, in order to basically implement that, we are using something called trigger rule. When you check it, it's either yes or no, basically. You know, it's kind of like the trigger rule. It should be all success, for example, all done, something like that. So start with the same thing, enabling pickling, define an argument. We are defining a DAG, give it a name. Here, a schedule interval, this means every minute. Every minute this will run. Catch up false. I give it a tag just for the querying to make it easier. Also, these two are, this last line and these two are identical. I just to show you how you can use this. Sometimes when you build these tags and this Airflow, like maybe it's shared across the environment and you want to know, okay, whose DAG is this? You know, you see lots of, for example, DAGs. So you can add an owner. So here basically says that if this DAG, the owner is me, and this is the link to the project, for example. That's the idea. You can either do it that way, or you could basically do something like this. Use the bash operator and basically add the owner to the scene. You know? So it's just to show you both ways it can work. So then we start with an email operator. So the idea of email operator is that we want to basically be able to send that email. So you give some task ID, a name basically, to this address. Okay, I want to send an email to this address. You can send it to someone else, but I will send it from your email. What's the subject? You give it some subject, and if you want to put some HTML contents, like what to be the text of that email. And this is going to be part of this deck. Okay, so that's the email operator, basically. Then, okay. Then we go back to the same thing that we saw before, all these steps one at a time. So I'm just going to skip through that as it's the same. Actually, there's one new function I added here. this function separate data outputs. Sometimes, let's say, you remember I said that when you pass data between tasks, we use something called pickling, right? What if you want to unwrap that data along the way? So basically, let's say you only want to work with pieces of that data. So you can use something like this. So TI XCOM pool to get from this task, you get the output and you break it down into the 4 data points. And you pass that to the whatever, wherever you're using it. So that's just an example for you if you want to get the intermediate data because they're pickled. How can you basically extract this? You can just use this TI XCOM pool. Give the task ID, and depending on how many data point you expect, how many variables you expect to receive, here I was expecting 4, I get all the 4. So, okay, this is the just Python operator, same thing over here. Then it goes to the last one, trigger DAG run. So we have already a DAG for the email, we just want to work DAG for this one, the trigger DAG run. So here basically we say, give it a name, and what should be the trigger rule? Under what condition I should make a call to the other one? And we remember we imported that trigger rules. And here I say all done. You could put all success, all failure, all done. Just put all done for the simplicity. And you say, okay, when it's all done, what's the name of the other DAG that I need to trigger? And this is the name of the other tag. We haven't created yet, but when we create it, this should be the name. Remember, Airflow will detect all the DAGs within the folder. So it need to find a DAG with this name, main DAG, the main canvas to has this name. And then we create the dependencies basically this way. So dependencies here is that first I set the owner, then I load the data pre-processing, everything. And when it's done, I send the email. Then I trigger the DAG run, basically. So that's the order. Is any question on that? Yeah.
In that case, how is it possible in the dependencies case? Like in the dependencies, it's only one way.
No, it's actually, that's a good question. No, so if you want to have, like, if you put something like this, that becomes like this scenario. If you create an array, that becomes like a parallel, basically, when the dependencies is not sequential. But it should be a DAG. DAG is order. Remember, DAG is the type of graph that has order, basically. You know, that's the part that's important. But it doesn't need to be everything secret. It could be some of this could be like a parallel. So let's go to the Flask API. Now we want to create a Flask API, but also be a DAG because we need to trigger it. So we import the DAG run. We import this. Let's say what are we importing? So this API, okay, this API, this DAG will run an API for me. Whenever this one activate this DAG starts running, and this DAG either way will run an API for me, so I can access this API. But what I wanted was the goal was that if I access this API, I want the page that I will see be dependent on what happened in the previous DAG. If the previous DAG, everything was successful, okay, no, there was no error. If I go to this address, I want this to redirect me to a success page. If it was a failure, I want this to take me to a page called failure. 2 different route, basically, right? So in order to do that, I need to import the DAG run and a state. A state is like if I make a call, hey, what was the state of the previous DAG? Was it all successful, all done, and something like that? That's the idea, to getting the state of something, right? And DAG run is helping you to search. So if I want to search across all the DAGs that was running in my environment, using a DAG ID, you need that function, DAG run. We will see how we're going to use it. So you just need to pass a DAG ID to it, and it will give you the result. And you convert that result from the state to, like, was it yes or no, successful or failure. So Then these are for same thing for the Flask that we saw, and then we all need a Python operator and a DAG. So we start by creating the same stuff. Here I create basically a Flask. This time I didn't use that basically static because I don't have the images. I just create a Flask API. Then you define a root. Now the root was the idea. User doesn't know, go to this page or go to this page. User goes to the main page, right? The main root address, which is this one. But if user goes here, I want the API itself redirect user to either success or failure based on what happened before. So we need a function. This function is defined here. Check DAG status. Let's look at this function. It basically looks at the DAG that we are trying to look at the status. It uses the DAG run to find that and to return the state if the state was success. So that's kind of like if condition. If a state was success. So if a state was success, it will return true. Otherwise, it will return false. That's the condition. So if DAG runs, that means if true, will return true, else it will return false. So I use this function in my main page, like main basically root. I will, as soon as user come to this page, I check with this function. And this function, if it was successful, I will say to redirect me to a page called success. If it was failure, direct me to a page called failure. Does that make sense so far? So we haven't defined a success failure yet, but this is just a redirection. Then that's where we're going to define the success and failure. So we define two new basically roots. One called success, one called failure. If we get redirected to a success, it uses that same thing that you saw, render template, and there's an HTML file, and it's just going to open that. If it was failure, it basically renders this HTML file and shows that to the user. Okay, so those are the two root addresses that we define. Then we need a function to start the Flask API. So we create this function. Why do we need a function? Because we're going to put it in a DAG, so we need an operator for it. So we wrap it in a normal Python function. And whenever you call to that function, it will run using the Flask API app.run on this address on this port. Okay. Now we're going to define our DAG. So we create a DAG. We give it a name. Some task, what we want, there's no interval because this one doesn't run. It depends on the other one. So there's no interval. And we give it some task. Then we call to a Python operator that is going to run this for us. Start Flask API. Because all you need to do is to run this. If you run this, that means your API is running. If your API is running, by default, this is running, this is running. This is basically will work because this is running. You see, so I don't need to connect any, those are already connected. So all I need to do is have one DAG that has this Python operator. And then there's no other dependencies. All I need to just have this start Flask API. And I put that in basically what's called the CLI, like I said, start Flask API for automatic start basically. So now I have two DAGs, right? They are connected with each other. Does that make sense before we continue? So let's do, actually, maybe I should have done earlier. Should have probably ran the we need to let that go. So the idea basically here is that when this is running, and think about how you can utilize this as part of your project or what you're building. You have a pipeline. This pipeline doesn't need to be simple like what we have here, more complicated. You basically automate your pipeline on a schedule. We could automate it based on trigger, right? Pipeline runs. You also have intermediate steps. You have a notification. If something went wrong, you get notification. Or maybe you can simply create an API. So instead of working with the Airflow, You just connect to this API and API has whatever page necessary for giving you the information, the insight that you need, right? So you can basically use something like this, simplifies some tasks or some processes. You can connect it to your, we have connected to our, what's it called, Slack. So you can connect it to a Slack if you want to get a Slack message. You can connect it to a text. You will get a text message. You can also connect it to your emails. It has Outlook and Gmail. We have tried, at least the students have tried. I don't know what are the connections it provides, but so let's do this now. Docker Compose up. So we let this to run. And what we will see here, when this comes up, you should see two DAGs on the Airflow dashboard. And one of them is basically every minute basically can run. If you set it on automate, but I think by default mine is on not automate. But if I trigger it, it will automatically start the second one. And we will see that this, when the second one starts, and if it doesn't end, because the second one, that's also something to keep in mind. We're creating an API, that API stays on. So it doesn't terminate. It basically just is always on. So if you want to use something like this, you need to think about that. I cannot turn off that machine because the API will go down. Right, so you just that's just a downside here to keep in mind. But if you're hosting on this on a cloud, then the API always could basically run. Right, so it's just if it's local, then API won't run always because it depends on your machine, the state of your machine. So almost done. Actually, I already got the email notification. I get something like this. Quickly, this is a notification email sent from Airflow, right? Because it ran in the background. It already sent me the email. So now, if I go to, where is the? Let's see what's the address. No, let's see. Let's see what port did we? Right. So, okay, so you see the you see there are two over there, right? And one of them is already running. So I'm going to pause this. Here. So I have two. One of them runs on a schedule. One thing that you see here is that you see Airflow owners. You see the in front of it, it says owner. If I click also on owner, it takes you to the address to the project. So that's one thing. But so if I run the first one and I look at the graph, And see now we have a much, here you see this dependency, basically this runs independent of each other. See this one? But as soon as I get it goes to the send email. I get the email quickly, like, hey, it did run or it did not. And then it will trigger the next step. Now, if I go back to the first page, this is running, you see the green. And that's because it was triggered by the previous one. So if I go on it, go to grab, this one is running. You see the state says, sorry, you cannot maybe see the running. How could we access that API? So if I go to this file, look at the log, for example, that's the address to the API. So if I click on that, the API comes up and it has the model training was successful. This is the date and this is right now the time. And again, you can do a lot more on this page, you know, whatever you want to create, redirect and stuff like that. But that becomes the main idea. So you can use a tool like Airflow, something like this, for orchestrating tasks to make it much easier. Because if you think about from dependency perspective, and this task basically that you're running, so if you don't have a proper orchestration, you need to do this manually and you need to always go back to see that what did happen and stuff like that. You just always worry about that if something doesn't work. And now if you have a pipeline, that's pipeline is an ongoing pipeline. Now data comes and you need to process it as it goes. So you need a proper orchestration tool. That's why Airflow is kind of like a pretty popular among these companies. And there are other tools out there, like it's not just Airflow, but this one is like a kind of like open source is popular. However, what we will see later, it's because we use GCP in this class. So Airflow being offered on GCP as called Cloud Composer. And it's unfortunately, it's pretty expensive when you run it for the class. So if you're planning to use Airflow as part of your project, every semester students, they end up with a problem because they ran Airflow as Cloud Compose, as a cloud service, and it was super expensive. If you want to do that, other basically students, what they did, they used the same Docker Compose and ran it as I don't know, like on a server, compute server, instead of using Cloud Composer, which is a predefined or pre-built by GCP. You just rent a compute machine and you run the same thing that we did in the class, and you just get the connection IP port that you need. So don't use the Cloud Composer if you are worried about the cost and you're going to run multiple times, like you want to do a try and error. Do it locally and then basically migrate it to the cloud.